Okay, so in two variables, x and y, we said that a one-parameter Lie group of transformations is given by, say, g star, your parameter acting on the variables x, y to give us x bar, y bar. We also showed that if you write x bar up to first order, you get x plus your parameter xi, and of course you've got higher powers of your parameter. G bar will be y plus g eta plus higher powers in your parameter. This is using an expansion. And we of course notice that the coefficient of g to the 1 provides us with the coefficients in the vector field that represents the tangent vectors to the curves of this one parameter Lie groups of transformations, i.e. the vector x, vector field x is xi d by dx plus eta d by dy. We can determine xi and eta directly from what we've done previously. That is that xi, of course, is exactly equal to dx bar dg evaluated at g equal to 0, and similarly eta is dy bar by dg evaluated at dg equal to 0, etc. Now we're going to consider something that's going to impact on finding the invariance of differential equations. If you consider any differential equation, right, we have a function involving the independent variable x, the dependent variable y, the derivative y double dashed equal to 0, say. For example, we have the simple harmonic oscillator equation y double dashed plus y equal to 0. So this is then the function e on the left hand side. So when this function e equals 0, you end up with a differential equation. But what we're going to look at before considering the differential equation aspect of it is to discuss the invariance of these kinds of functions. That is, functions in which one variable depends on another variable. So we're going to regard this, and as example, there's a function y double dash plus y. So that's a function, but a function of possibly xy, independent variable, dependent variable, y dashed, which depends on x, y double dash, which of course will depend on x, and of course you can go higher. We'll call these functions on the left hand side differential functions, seeing that they may contain the derivatives of the variable y with respect to the independent variable x. So essentially we're going to look at the invariance of these functions. When these functions are put equal to 0, we will look at the invariance of the differential equation. But to do that, we need to extend our understanding of the manifolds that we've been looking at thus far. Keep in mind that what we have here that's different from before is the fact that this y is no longer, I want to do this in black, is no longer an independent variable from x. You've got y is some function of x. And if y is a function of x, then you know very clearly that all derivatives of y are some functions of x also. So this could be a function of x, and y double dashed is a function of x, etc., etc. So the function y and all its derivatives are functions of the original variable x. However, we're now going to introduce the notion of a jet space. The jet space is the space that is embedded in some manifold wherein the coordinates are your usual x variable, your y variable, and the other pseudo-independent variables that form the other coordinates in the Cartesian system or the submanifold are y dashed. If you want to think of that as p, then of course there's another axis there represented by y double dash. You may want to call that q. So that if you have a differential function, let's suppose your differential function is something like x, y dashed plus y double dashed plus y squared, say, then you may construe this function e, the differential function, as being a function of four variables, namely x, p plus y, q plus y squared. So this is a function now of four variables, where you need to keep at the back of your mind that the variables y dash, y double dash are variables in their own right. So the thing here to keep in mind is that on the one hand, y is a function of x, and so too is y dash and y double dash, but we're regarding them also as independent variables in their own right. This system of thought is operating in this space that we call a jet space, and we now have a manifold. For example, what this function e of x, y, p and q, or x, y, y dash and y double dashed, is operating as a subset of R4, or in a subset of R4. So it's a frame, it's a surface in R4, and therefore it's a manifold in R4. As a result of that, we need to now define or extend our notion of a one-parameter Lie group of transformations on, say, G star, say on just xy, to be G star on x, a third variable y dashed, and a fourth variable y double dashed, etc. So that this would then be x bar dashed, y bar double dashed. On the right hand side, dashed is with respect to x bar. So that now, if it's a one parameter Lie group of transformations, in other words, in the jet space, then the tangent vectors have an equivalent vector field representation given by xi d by dx plus eta d by dy, and of course xi here could be a function of x and y, and eta could be functions of x and y. But now we're extending this vector field to take account of the additional variables y dashed and y double dashed. So we have some coefficient of dy dashed and another of dy double dashed. And what we need to do now is, since these y dashed, y double dashed, etc. depend on x, we need to now determine the forms of the coefficient of dy dashed and dy double dashed in some way. Well, remember we said that x bar in its expansion has a coefficient of the parameter g given by xi. Similarly, y bar in its extension, written in this particular form, has the coefficient of the first power of g being eta, the very exciting eta that comes from the vector field. Therefore, to determine the coefficient of dy dashed in the vector field and dy dashed, double dashed in the vector field, we need to expand y bar dashed and y bar double dashed and determine the coefficient of g. that will give us the respective coefficient of dy dashed, and when we expand y bar double dashed and take the coefficient of g, that should give us that term in the vector field. Right, now before we do that, I'm going to define the notion of total differentiation, total derivative operator, as opposed to partial derivative operators. Now if you differentiate a function partially with respect to x, you're regarding y, and of course in this case y dashed, y double dashed, as independent separate variables, as constants. So first of all, note that if you have e is equal to x y dashed plus, I'm just giving an example, y double dashed y squared, then if you were to do the partial derivative of e with respect to x, right? So x is a variable, the rest are constants. So you got 1 times y dashed, and of course derivative of y double dash y squared partially with respect to x is 0. Similarly, if you did the partial derivative of e with respect to y, you'll get 0, there's no y's in there, and then you got y double dashed, derivative of y squared is 2y. Well, let's do one more. If you differentiate e with respect to y dashed, you get x times 1. There's no y dash in the second term, so the derivative is 0. And for completion, if you differentiate e with respect to y double dashed, you get 0 plus 1. Derivative of y double dashed with respect to itself is 1 times the constant y squared. However, if you were to differentiate the function e totally with respect to x, then you would apply all your rules of differentiation, product rule, implicit, etc. So that when you differentiate this function there, e totally with respect to x, then what we get is the following. You've got a product rule on xy dash, which is 1 times y dashed, plus x times, if you differentiate y dashed, you get y double dashed. If you differentiate now the second term, the derivative of y double dashed totally with respect to x is y triple dashed times y squared, plus if you differentiate y squared totally with respect to x, you've got to apply implicit differentiation. So you've got 2y times the derivative of y is y dashed. Note the difference between the total derivative with respect to x and the partial derivative with respect to x. And of course there's the possibly other partial derivatives. We will show that by the total derivative operator, you can get the same total derivative with respect to x by utilizing the partial derivatives that we've done there. Okay, and it's essentially a consequence of the multivariable rule for the multivariable chain rule. We know that, for example, e could be a function of x, which is of course a function of x. Y, it's a function of y, and y in turn is a function of x. E could be a function of y dashed, which could be a function of x, and e could be a function of y double dash, which is a function of x, and of course we could go on. So that if you wanted the total derivative of e with respect to x, the chain rule for multivariable says, starting with the first arm, it's the partial derivative of e with respect to x times the derivative of x with respect to x. Then from there, it's the partial derivative of e with respect to y multiplied by the derivative of y with respect to x. That's that part. If you differentiate y with respect to x, you get y dashed. Now going into that arm, differentiate e with respect to y dashed, multiplied by the derivative of y dashed with respect to x is y double dashed, plus going lastly into that, differentiate e with respect to y double dashed, times the derivative of y double dashed with respect to x is y triple dashed. And of course, theoretically, this goes infinitely far. So that therefore, if we drop the e, the total derivative operator is the infinite operator d by dx partial y dashed d by dy plus y double dashed d by dy dashed plus y triple dashed d by dy double dashed, and that goes on infinitely far. When it operates on a specific function, it becomes finite. This is what we define as the total derivative operator. Right. Now to go on to finding the vector field x that could possibly contain the derivative terms. And the starting point is the following. So we want to expand y bar dashed. Y bar dashed is the total derivative of y bar with respect to x bar. By the chain rule, this is the total derivative with respect to x of y bar divided by the total derivative with respect to x of x bar. The y bar and x bar I'm going to use is the expanded form we have here. You notice if you differentiate x bar with respect to x, you get 1 plus g times the derivative of xi. And if you differentiate y bar with respect to x, you get the derivative of y plus g times the derivative of eta. Keep that in mind. So this is then equal to the derivative of y bar is the derivative of y with respect to x totally plus g times the derivative of eta. So this is the derivative of eta with respect to x. If you differentiate x bar, you get the derivative of x with respect to x is 1 plus g times the derivative of xi with respect to x is given by that. I need not do any terms involving g squared, etc. All I need is the coefficient of g in this whole expansion. Right. This is, if I expand this using the geometric series at the bottom, right? So if I expand that 1 over that, I get 1 minus g times dxi dx plus of course terms that are higher order in g. So this is equals that. And when I do this multiplication, I get y dashed plus g into d eta dx minus y dashed dxi dx. These are total derivatives, plus of course terms involving g squared, etc. And you notice this is the coefficient of g, so that in the vector field, the extended vector field x, namely this term there, is what I now have determined. And similarly, if you do the expansion of y bar double dashed, you will take the coefficient of g to get that term. So that therefore, the vector field x, now in its expanded form, is equal to xi dx plus eta dy plus what I'm going to call eta 1 d by dy dashed, where eta 1 is this term we've just constructed, the total derivative of eta with respect to x minus the total derivative of xi with respect to x. And of course, we can expand this. I'm not going to do the calculation. If we call that eta 2 d by dy double dashed, then eta 2 is, we can show the total derivative with respect to x of eta 1 minus y double dashed, the total derivative of xi with respect to x. We will call this x x2, like so. So thus, the vector field prolongation, extension of the vector field x, namely x1, x2, etc., given by this, which represents a one-parameter Lie group of transformations, x bar, y bar dashed, y double dashed bar, etc., is of this form, where the eta ones are respectively given by that. There's the eta 1, and the eta 2 is given by this function here. And now we can speak about invariant functions. We can check which functions are invariant, differential functions that are invariant under these prolonged vector fields. So if I go back to, say, a function of this type, where is the function e? Let's consider this function e of x, y dashed, y double dashed, y squared, for example. So I can ask a question like, is the function e equal to, say, x, y dashed plus y double dashed. This is a differential function containing up to second order derivatives. Is a function like that invariant under some one parameter Lie group of transformations? Let's say, is it invariant under, as an example, say, the vector field x, which represents a one parameter Lie group of transformations. Let's give it a name, x dx, and this is just a random example. Let's make it 2y dy. Well, to do that, I'll have to check if x on e is equal to 0. To check for x on e equal to 0, I have to prolong x first. So first of all, I'll have to determine e1. Note xi is x, that is xi, and eta is minus 2y. So eta is the total derivative with respect to x of minus 2y minus y dashed, the total derivative of xi. So this is then minus 2y dashed minus y dashed times 1, which is equal to minus 3y dashed. I will need eta 2 because there's a y double dash term in e. So this is the total derivative of eta 1. That's a bad x. This should be x. Total derivative of eta 1 minus y double dashed, the total derivative of xi. Now here is eta 1. If you differentiate it totally with respect to x, you get minus 3y double dashed minus y double dashed times the total derivative of xi, that is 1. So this gives us minus 4y double dashed. So that, therefore, the operator, the vector field x2 is equal to x itself then eta 1 plus times d dy dashed. So this is minus 3y dashed d by dy dashed, and then eta 2, which is minus 4y double dashed, d by dy double dashed. And therefore then we do the operator x2 now in terms of partial derivatives operating on e. And remember, the x2 in this form is a partial derivative operator. So when you differentiate with respect to the variables x, y, y dash, y double dash, the rest are treated as constants. So there is e. So we have, this is first of all x times the derivative of e with respect to x, we had this before, is y dashed, minus 2y. The derivative of e with respect to y is y double dashed times 2y minus 3y dashed. The derivative of e with respect to y dashed is x minus 4y dashed minus 4y double dashed. The derivative of e here with respect to y double dashed is y squared. And clearly this is not going to equal 0. Maybe it did, let's check. No, it's not. And this is definitely not equal to 0. Therefore, e is not invariant. It's not an invariant function. It's not invariant under this vector field x. We don't say x2, we just say x. If it was equal to 0, e is an invariant function. So now we have dealt with functions containing derivatives, where we assume one variable is a function of another variable. We have a jet space, and we've spoken about one parameter Lie groups of transformations in this jet space, and defined vector fields therefore in this extended system of variables, and then extended the definition of invariant functions to invariant differential functions under vector fields. We can now speak about when a differential equation is invariant under a one parameter Lie group of transformations, or equivalently when a differential equation is invariant under the corresponding vector field.